Hello everybody and welcome to yet another math video. In this video I'm going to be going over systems of linear equations and matrices. I've got to start out with matrix basics just so you know what they are. You have to know what you're working with before you start working with them. Then we'll hop over into what augmented matrices are. We'll touch on coefficient matrix very quickly, but more we're interested in augmented matrices. And then we will dip our toes into the pool that is Gauss-Jordan elimination. We are focusing on two equations with two unknowns. So let's get into it. Matrix basics. This is going to end up being a lot of vocabulary. So first, matrix, what is it? It's a rectangular array of numbers. Pretty easy. You can see that these examples here, we use capital letters to represent matrices. You can see these two matrix examples, matrix A, matrix B. They kind of look like rectangles here. And with rectangles, you would be able to tell that they have dimensions. So one thing that's really weird about matrices is that you can kind of think of these matrices as also having an area, but this matrix has an area of 12, right? It's 3 tall and 4 wide, and this matrix also has an area of 12. It's 6 tall and 2 wide. But these matrices have very different dimensions. Even if you had a matrix like this down here, matrix C, this is 2 tall and 6 wide. These matrices B and C are very different in their dimensions. Even though all of these matrices have the same area, they're just very different. All right, so how do you figure out what the dimensions of a matrix are? Well, very easily stated, a row moves from left to right. So in matrix A, here's 1 row, here's 2 rows, here's 3 rows. There are 3 rows in matrix A. In matrix A, columns are vertical. So rows are horizontal, columns are vertical, top to bottom. So here's column 1, column 2, column 3, 4 columns. And how you represent dimensions would be rows by columns. So we would say this matrix has dimensions 3 by 4. Okay, so we can do something similar over here for matrix B. Matrix B has 1, 2, 3, 4, 5, 6 rows. And matrix B has, you can see here, 2 columns. So the dimensions for matrix B would be 2 rows by 6 columns. Oops, I did that wrong, didn't I? I want to say 6 rows by 2 columns. 6 by 2. There we go. I guess I had example C on my mind. So matrix C only has 2 rows, and I think you can see it has 1, 2, 3, 4, 5, 6 columns. So this would be a 2 by 6 matrix, we would say. So that's how we define the dimensions of a matrix. Also, we can pick out different elements in a matrix. An element is just an expression. Elements are expressions that appear in a matrix. So this 3, that's an element. This a minus 4, that's an element. This negative 86, that's an element. It can have variables. It can be a constant like e squared. E to the second power is, in fact, a constant. But we can look at the elements. The lowercase letters correspond to the capital letters that represent the matrix. So if we're looking for element A subscript 3, 2, we are looking for something in matrix A, and we're looking for what will be in row 3, column 2, just like we do the dimensions. This is like where's the location in rows first and columns second. So if we go to row 1, 2, 3 and go over to the second column 1, 2, this answer here will be 5. So again, we can do the same thing over here for matrix B, and I know we're working with matrix B because the lowercase b matches the capital B. We can go down to row 4 and go over to column 2 and find out that this one is R. All right, more matrix basics. So in this slide, I will be going over square matrix, column matrix, row matrix, and the principal diagonal. And to be fair, a principal diagonal works more with a square matrix best. It works best with a square matrix more than anything else. So let me get examples of these up on the screen. So here are examples of each of the types of matrices I've listed up there. The square matrix, no surprise here, it should look like a square. The number of rows should be equal to the number of columns. So any matrix that has an equal number of rows and columns, it will be a square matrix. A column matrix, underlined in blue, here in blue, will be a matrix that consists of only one column. So it can have as many rows as desirable, I guess all the way up to infinite number of rows, which is just weird to think about. We'll keep it finite, like 5 rows, 1 column. As long as there's only 1 column, it's a column matrix. And something very similar for row matrix, underlined in green, here in green. A row matrix will only have 1 row. Now the last bit of this here, the principal diagonal. The principal diagonal in, I guess it's any matrix. I know for sure it's a square matrix. The principal diagonal for a matrix will always start in the upper left-hand corner and just move down diagonally. 1 down, 1 to the right, 1 down, 1 to the right. You can see it just sort of almost follows like a slope pattern here, a -1 slope. So here is the principal diagonal. And that's it for this slide. Let's move on. All right, we actually get to do something interesting with matrices now. So similar to solving by elimination or by addition, you want to make sure, or we can say if all equations have all variable terms on the left side and all constant terms on the right side, then you can find a representative coefficient matrix or augmented matrix for this system, for a system of equations. That being said, here we have all variable terms on the left, all constant terms on the right side of the equation. And you'll notice again that we have x's first and y's second. Fantastic. And that is going to be super important because when you make a coefficient matrix, coefficients are numbers, are constants that are multiplied to variables. So we can see that the first coefficient we have will be 4. The next coefficient that we will have will be -3, and that's a y coefficient. So that will start a new column. So we can think of each column as representing a different variable. And that makes things very easy to line up. So the next equation, -1, will start a new row. -1 for the x, 9 for the y. So here is the coefficient matrix for our system of equations. We have the first equation like we do and the second equation like we do. They turn into rows in the matrix. So again, you can see in the first equation, 4 and -3 represent 2 different variables, so we put them in different columns in a matrix. But the row represents the first equation. The second equation represents the second row, again with x's first and y's second. Now an augmented matrix is a matrix, just based on the word augmented, Augmented means to make bigger. So we're going to take this coefficient matrix and make it bigger. And what augmented matrices do is they represent an entire system of equations, including the constants, not just the variables. So coefficient matrix, just the variable stuff. Augmented matrix, the entire equation, including the equal signs, which is pretty cool. So the augmented matrix starts out with things that we're familiar with. The coefficient matrix is a part of it. But the augmented matrix adds in the constants that are also in the equation, so 14 and 1. And how do we know that this last column is the column of constants? Normally, we put a vertical bar in between the coefficients and the constants. And this vertical bar generally means that we will have equal signs there. So you can almost see it. You've got 4x, and the 4 is here, minus 3y equals 14. Negative 1x plus 9y equals 1. So you can pretty well see, normally we will not be writing the x's and the y's that are above these two columns, so you'll just have to know what variables you're working with. And lastly, the coefficient matrix is not always going to be square. It generally will be square, but it ends up being the number of rows. And you may have noticed that there was some switcheroo going on down here. The number of rows would be equal to the number of equations, and the number of columns would be equal to the number of variables that you have in your system of equations. And in augmented matrix, the number of rows still is represented by the number of equations you have in your system, but the number of columns is represented by the number of variables you have, plus one more for the constants. Now that you have some idea as to what augmented matrices are, let's take a look at Gauss-Jordan elimination and the basic idea behind it. Gauss-Jordan elimination, first we're going to start off with an overview and then go over row operations. So Gauss-Jordan elimination is a way to solve systems of equations using matrices. Here's the basic idea. You have a system of equations that you turn into an augmented matrix, and you can see there's row 1, row 2, row 3. And again, I said I'm not normally going to write these variables up here, but I'm doing it here for another reason. The first column would represent x's, second column y's, third column z's would equal these constants. Fine. Another way to represent variables a lot of the times in matrices or in systems of equations is to only use the x variable, like you see down here. We could call this x sub 1, x sub 2, and x sub 3, where sub just means that these are subscripts down here. But x1 is different from x2. These are two different x values, and x3 is a different value from the other two. So none of these x's are the same. That's why they have these little numbers down here to let you know that they're different. So what happens with this augmented matrix is that through a lot of row operations and minor headaches, we will get a matrix that looks like this. This is what we call a reduced row echelon form matrix. And we know that this is reduced row echelon form because on the principal diagonal, we have all ones, and everything above and below those ones is 0. So in this column, we have a 1 in the top and then 2 zeros underneath. In this column, we have a 1 in the middle and zeros above and below. In this column, we have a 1 in the bottom position and zeros above. That's how we know it is reduced row echelon form. Why is this so important? Well, when we get reduced row echelon form, our answer is plainly laid out for us. This column then represents our answer. And as you can see, just as a quick example, with this first row being an equation, remember? This is 1x plus no y's plus no z's. So this is just x equals -2. This row would represent y equals 7. This row would represent z equals 13. And that's it. We would write our answer out as, in this case, an ordered triple, -2, 7, 13, in a set of parentheses. So what are the row operations we use to get there? We have 3 different row operations. We can do a row swap, which means we just replace, we switch around 2 rows. Like I could swap row 3 and row 1 right now. And the bottom row would become 1, 2, 3, 4, and the top row would become 7, 8, 9, 10. We can multiply a row by a scalar as long as it's not 0. So I can multiply row 2 by 4 if I want, and it would become 16, 20, 24, and 28. And that's just something we can do. We can multiply a row, some row, by a scalar as long as it's not 0, and then we replace that row again. And then we have a row combination, or what I call a row combination. That's where we multiply a row by a non-zero scalar, add it to a different row, and replace that different row. You'll notice these are the same. And these row operations make a heck of a lot more sense when you see them in action. So I'm going to stop talking about them for now, except for one more thing here. These row operations are good for ones, and you'll notice again that ones are very important in matrices. And this last row operation is good for zeros, and again, zeros are going to be very important to get in our matrix. So knowing how to get ones and zeros will be very helpful here. Let's take a look at some special matrix glitches that you'll see along your travels in math. So matrix basics, some special solutions here. Let's say that you're simplifying a matrix using row operations, and you get a row that is all zeros to the left of your vertical bar, and any number but 0 on the right. If this happens, there will be no solution for your system of equations. However, if you end up with a row of all zeros, and it can happen anywhere, it can happen in the bottom row, middle row, top row, and the same thing with this, it can either happen in the bottom row, top row, middle row. But if you get all zeros, that means you have infinitely many solutions. So you have to be on the lookout for these 2 types of rows. All zeros and the last number is not 0, and all zeros. All right, let's take a look at some examples for real. Here we go. First example in solving by Gaussian elimination. So this example will probably take a while because I want to get through the entire process, how you work through it, how you think through it. So without further ado, let's get into it. The first thing you want to do is make sure that the equations are set up correctly. Again, you want all the variable terms on the left, and you want the variables to be in the same order in all the equations. So the x is first, the y is second. You could actually do the y's first and x's second if you want to. It'll have a very similar effect on the solving process. You want to have the constants on the right side of the equation. From there, you can make the augmented matrix, which again, remember, is the coefficient matrix. And then we augment it, aka make it bigger, by putting the constants on the other side of a vertical bar. So just like we had equation 1 and equation 2, we have row 1 and we have row 2. And I'm not going to continue writing row 1 and row 2. We just know the top row is row 1, the next one is row 2. If there are more rows, then there are row 3, row 4, row 5, row 6, so on and so on. So with this, how Gaussian elimination works, all you know right now is that it needs to be, we need to have ones on the principal diagonal and everything else needs to be zeros. So how do we get a 1 up there? Well, we have to use the row operations, and it looks like we already have a 1 in the first position for the second row. And if we just do a quick row swap, we will have a 1 in the top row. So what I'm going to do is I'm going to write, this is row 1 swapped with row 2. Very cool. So what happens, row 1 is now 1, 2, 10, and row 2 is 3, -1, and 2. There we go. Next, what we need to do is get, now that we have the 1 up here, and this is super important that we have this 1 up here, we need to get zeros below it. So getting a 0 below this 1 means we will have to use a row combination, as that is what the row combinations are good for. So we know that we're going to be adding 2 rows together, and we're going to replace the row where we want the 0. In this case, we want the 0 in the second row, so we will, replace, that's what this arrow means. We're just going to replace row 2 with all this stuff here. So how do we get this 0? Right now in its current form, this operation is telling us just to add these rows together. 1 plus 3 is 4, not 0. So we have to think, what number can we add to 3 to get 0? And that's an interesting question, because negative numbers are often forgotten, and we're adding. So adding a negative number just gets often pushed into a subtraction. So you guess you could think of it that way too. What 3 minus what number gives you 0 would be 3. But we would have to multiply the top equation, or the top row, by a -3 in order to get that -3 that we need. So let me go ahead and multiply the top row by -3. It's -3, -6, and -30. So you'll see that if you combine the -3 and the 3, we end up with a 0. So our second row then becomes 0. Here we have -6 plus -1, that is -7. And then we have -30 plus 2, which is -28. But the top row stays the same. And so we have completed what we set out to do. We have a 1 up here. And ultimately, really what you'll see is that it just ends up being the opposite of this number that you need to multiply by row 1. Right? The opposite of 3 is -3, so multiply row 1 by -3. But we did it. Our first column is done. We have a 1 in the principal diagonal and a 0 underneath it. Now we have to come over here and concentrate on this -7. After we get a 1 with zeros below it, we need to find the next 1 in our principal diagonal. So what can we do here to make a 1? Well, we can't row swap, because that'll move this 1 that we need to have here out of its position. We can't do a row combination, because that'll add things back into it. Row combinations are good for zeros anyway. That leaves us with multiplying this row by a scalar, as long as it's not 0. And really that extends over into division as well. So if we take row 2 and we divide it by -7, we just divide it by the number that's here,
we should get 1. And where are we going to replace? We're going to replace row 2. So there will be a new row 2 over here, which will be, let's see, 1, 2, 10 is row 1, 0, 1, 4 would be row 2. If you divide negative 7 by 7, you get 1. If you divide negative 24 by 7, you get 4. Awesome. So we got our next 1. Oops. We got our next 1 on the diagonal. There it is. We have a 0. Now with Gauss-Jordan elimination, we have to get zeros above the 1s as well. So we need this 2 up here to become a 0. Lucky for us, we can use a row combination to figure that out. We have a 1 here, so what we will do is we will take that row 2, we'll end up multiplying it by something, we will add it back into row 1 and replace row 1. And I hope you guys see this, that we need to multiply row 2 by negative 2, because that negative 2 is the opposite of what we're trying to make 0. So when you multiply the second row by negative 2, you get 0, negative 2, negative 8. And then we can add it to row 1. So here we go. So 0 plus 1 is 1. Negative 2 plus 2 is 0. And negative 8 plus 10 is 2. And the second row does not change here. That's it. We are in reduced row echelon form. We've used Gauss-Jordan elimination to its fullest. What does this mean? How do we interpret this? Well, the last thing we need to do here is tell everybody, hey, what's the answer? And I sort of made mention to it that this is the answer over here in the right column. But again, the first column represents the number of x's, the second column represents the number of y's, the last column is a constant, and this is equal, remember? So we have 1x equals 2 and 1y equals 4 as our new equations. So we have x equals 2 and y equals 4. So if we need to leave them separated out, you can. You can write it as an ordered pair. It all depends on what you're using the matrix for. So either one of these answers is good. Let's take a look at one more example. It'll be a lot shorter than this one. So here we go, one more example. We have this weird variable set up now, x1 and x2. Again, these are just variables. These little subscripts down here are just letting you know that these variables are different. So instead of having an x column and a y column, we'll have an x1 column and an x2 column. So here we go. We can set up the matrix. That would be 1, 2, 4, 2, 4, negative 8. Sweet. We need a 1 in the upper left-hand corner to start on our principal diagonal. Fantastic. And we need to get zeros underneath that 1 now. So we know we will be having a row combination because that's how you get zeros. So 1, row 1, plus row 2, and we're going to replace row 2. And I know I'm going to multiply row 1 by negative 2 because that's the opposite of the number I'm trying to turn into 0. Alright, so let's multiply row 1 by negative 2. That'll be negative 2, negative 4, and negative 8. And from there, we can add these red values to these black values. Okay, so negative 2 plus 2 is 0, and this will be going in row 2. Negative 4 plus 4 will be 0, and negative 8 plus a negative 8 is negative 16. The first row does not change. Oh. Here, this This is one of the rows I told you to look out for. If you have a row that starts out as all zeros, but the last number isn't, then this system has no solution. What this equation is telling you is you have 0x1s plus 0x2s equals negative 16. Well, this all just simplifies to 0 equals negative 16. That can't happen. So this gives us no solution. All right, that's the end for this video. I hope very much this video gets you some better understanding for Gaussian elimination. Good luck.